Great pleasure to introduce our next keynote speaker. Rich Caruana is a senior principal researcher at Microsoft Research. Before joining Microsoft, Rich was on the faculty in the computer science at Cornell University, at UCLA Medical School, and at CMU Center for Learning and Discovery. His thesis on multitask learning helped create interest in a new subfield of machine learning called transfer learning. So I think that had a huge impact and directly fed into like all the kind of topics that we're thinking about here at CoLLAs. Rich received the NSF Career Award in 2004 for meta-clustering and co-chaired KDD in 2007. And with that, I'm going to give the floor to him. Thank you.
Hey, thank you for the introduction, and thanks very much to the organizers for inviting me to the first CoLLAs. It's exciting to see a conference on learning to learn, lifelong learning, inductive transfer, and all those sorts of things. Hey, so what I'm going to do is I'm going to start off by giving a brief history of inductive transfer, focusing on inductive transfer before deep learning. Then I'm going to talk a little bit about the next step for me, which led to very large-scale multitask learning. And then at the end, I'll talk about some new stuff that's kind of exciting, which is glass box multitask learning. But let's get started with a brief history of transfer learning. Now, transfer learning has gone by many different names over the years. It used to be called bias learning. Of course, there's multitask learning. There's representation learning or learning internal representations. There's learning to learn, lifelong learning, continual learning, speed up learning, hints and rule injection, co-training. Hierarchical Bayes is how many people would like to refer to this in the statistics community. Meta learning, adaptive learning, never-ending learning, and I'm sure I've left off a dozen or so of these possible names. So it's really a complex collection of many different ideas, and each of these sort of has their own name. I went back and tried to find the earliest example of something that I would call inductive transfer or multitask learning. And the first thing I came up with was NetTalk, a system published in '86 by Sinowski and Rosenberg. And the way NetTalk works, I'm going to guess many of you may not have heard of NetTalk, is you have a sliding window on the input side of the neural network. And this sliding window is characters in text that you want to pronounce. So this is space, I, space, COUL. So it's probably about to say something like I could. And then the goal of NetTalk is to learn to predict the phoneme and stress on that phoneme for the character in the middle. So right now it's trying to predict how to say the C, and it could be a soft C like S, or it could be a hard C, more like a K, like K. So it's trying to figure out how to predict this particular letter in the middle of the window, and it has some context of the letters to the left and right of the letter it's trying to pronounce. Now, this isn't deep learning. This model only has one hidden layer, as all of our neural nets did back in the 80s and 90s. And this hidden layer is actually fairly big by standards in '86. It's got about 30 hidden units in it. So this is a fairly large network. And then what makes this interesting from a multitask learning inductive transfer point of view is it has many outputs. Instead of there's think of it as being, say, 50 phonemes and a dozen stresses that you might place on those phonemes, like rising and falling and soft and hard. And instead of trying to train, what would have been, say, 60 neural nets, one to predict each of those things separately, because neural nets can handle having multiple outputs, they naturally put all of the outputs at the same time on the network. Now, they're not using a softmax to try to distinguish between these different letters and stresses, because not all of these things are mutually exclusive. But they are learning all of these things simultaneously, and that's really interesting. Now, it turns out they weren't thinking about doing this in parallel because they thought they would get higher accuracy out of it. They were doing it for practical reasons because they really had to train all of these things at the same time. And in fact, a few years later, I analyzed NetTalk, and it turns out on the bottom here, we have the stress tasks, their accuracy as a function of training time on the x-axis. And you can see that the stress tasks are learned very quickly, and then they begin to overfit. But the phoneme tasks are learned much more slowly, so they take a long time to train. And by the time you get peak performance on the phonemes, which are very important, you've clearly well overfit the stress outputs. So it turns out from a multitask learning point of view, they really should have at least separated this into two separate networks, one for the stress outputs and one for the phoneme outputs, or they should have done something to adjust learning rates and things like that. But nobody was thinking about that back in 1986. Basically, these guys were just very happy that they were able to train a reasonably good model on this task, and it was a single neural net. And it was a really exciting demo, by the way, back then, because you could actually sort of hear this thing learn, because then they would connect NetTalk up to a box that would actually speak those phonemes. And you could sort of see early in training, it was more gibberish. Middle of training, it sounded a little bit like a child. And then later in training, it was becoming more performant. So it was a really exciting demo of the early success of neural nets. Okay, so that's Sinowski and Rosenberg's NetTalk. A few years later, Dieterich, Hild, and Beccari, they did an analysis of why did NetTalk work better on a neural net than it did with ID3, which is a decision tree package. And they said there were a number of reasons why the neural net was working better than the decision trees. But one of the reasons they thought was because all of these phoneme tasks were being trained together on one neural net, as opposed to with ID3, you were training separate decision trees for each of these. So this was an early recognition that there might be some advantage to training these things together. Then about that same time, we've got Siddharth Kyrgyostan and Holden and Abu Mustafa are both trying to inject bias into learning through the outputs of the neural net. And they're doing either what you would think of as rule injection, which is, oh, the output should be a function of this feature and this feature in this conjunctive way, or they're trying to give the model hints, such as you should be a monotone increasing function of something. So they're trying to basically help neural net learning through the outputs. Then Dean Pomerlew's famous Alvin, this is the first autonomous vehicle navigation system. And his system had an input retina of the road. It also had a rangefinder input retina of the road. And then what makes this interesting from an inductive transfer point of view is instead of having a single output, which was the angle that you should turn the steering wheel to stay on the road in your lane, Dean empirically found that by having many outputs, the ones on the left code for hard turn left, the ones on the right code for hard turn right, the ones in the middle code for go straight. By having a complex encoding spread among all of these different outputs, he found he was able to get extra accuracy than if he just treated it as a single regression problem. And we now know that part of the benefit from this was from an inductive transfer multitask learning point of view. So that's Dean's work. Then Lorian Pratt and the Sharkeys were both doing work where they were adding extra tasks to neural nets, but their goal was not improved generalization. The goal was to speed up learning because neural nets were really expensive to train back then, as they are now, but we didn't have GPUs and good software back then. So they were trying to just make learning faster. And sometimes they were willing to accept even a small loss in accuracy as long as learning was fast enough. Then Mark Ring, at about the same time, was working on what he called continual learning. He had a system called Child. And the whole idea was that the system would keep learning over time multiple tasks as it went forward. Then my work in '93 is perhaps the first work to really focus on what we would think of as single task learning versus multiple task learning. Like, what's the benefit of having multiple outputs on a neural net? Why is that better than having those outputs on separate neural nets? Why is it good to have this multitask framework? And it helps when the data tends to be small relative to the complexity of the function you need to learn, and when the representation you learn has to be general purpose. And this kind of work, we did it not only in neural nets, but we also showed the same thing in k-nearest neighbor and in decision trees. So that's my work in '93, I think is when it was first published. And then about that same time, my advisor was Tom Mitchell. and Sebastian Thrun was in Tom's lab. They worked on EBNN, explanation-based neural nets. And this is where you basically had information about what the model should be learning, and you were able to inject that base back into the model. And by doing that, sometimes get extra generalization accuracy out of the model. And then Virginia Desau's work was on minimizing disagreement. So basically, she would have one neural net that's learning, say, from acoustic signals, and another neural net that might be learning from visual signals. And if they were learning similar related tasks, she wanted what was learned by one neural net to have similar prediction classes as what was learned by the other neural net. So she was minimizing the disagreement between these two independent neural nets. So they didn't share a representation, but what they shared was the predictions they were making, and they tried to inform each other, kind of like a co-training situation. Then Jonathan Baxter started doing some work in representation learning and in theory of representation learning. And then Thrun and Mitchell came up with their work on learning one more thing, which is serial multitask learning, serial inductive transfer. And Schmidhuber started doing some work on these learning to learn strategies. Then going forward, Diederik and Bakari, who had done the analysis of NetTalk, they did this error correcting output code stuff. And that's kind of cool. So instead of having a single output for each class, they use a complex encoding that has multiple output units on the neural net to code for each of the classes. So you've only got 10 classes, you only really need 10 outputs, but here they're using 14 different outputs and a complex encoding to represent each of these classes. And part of the advantage is you get this error correcting idea, which is of course the name of the method, but you also, it turns out, you get a multitask benefit by doing this. You're learning multiple related yet slightly different functions, all for the same thing, and this helps learning generalize better. So then we've got even Breiman, Leo Breiman, who's famous for bagging and for random forest. Breiman and Friedman did some work in statistics that they called Kurds and Way. It's sort of a statistical approach to multitask learning. And then we've got Sebastian Thrun doing some more work on lifelong learning. I believe this might be Sebastian's thesis. And then Danny Silver started working on parallel transfer with neural nets. Sebastian did some work with Joseph O'Sullivan on task clustering. So this is doing multitask learning in k-nearest neighbor and figuring out how to use the relationships between these tasks to cluster them. And then I did some work again with Virginia Desau, and here we showed that, you know, sometimes it's better to take things that could be used as input features and instead use them as extra output tasks, and you can get improved generalization by doing that. And then Monroe and Parmanto started working on committee machines, which is you again have multiple outputs on a neural net, and you have a way of voting these outputs to get a prediction. So think of this as a combination of ensembles and multitask learning all happening in a single neural net. And then Avram Blum and Tom Mitchell did this work on co-training, which is a form of inductive transfer where these different models are informing each other. And then Ben David, Johannes Gerke, and Schuller did this work where they were trying to do a better theoretical analysis of multitask learning, which is very difficult to do a theoretical analysis of MTL. And then Baker and Heskes started trying to push this into Bayesian methods, leaving neural nets in k-nearest neighbor. And then Tony Jabara started doing multitask learning in SVMs and trying to figure out, you know, what's the best kernel for these multiple tasks. And now we start to see more work in kernels because SVMs were very popular at about this time. And finally, we start seeing multitask learning happening in Gaussian processes in GP. And this was the info vector machine by Lawrence and Platt. And then Yu, Tresp, and Schweighofer are starting to do even more multitask learning in GP just about the same time, although their algorithm is different than the info vector machine. And then deep learning happens. So I'm not going to try to summarize all of multitask learning, inductive transfer, since deep learning has happened. The cool thing about deep learning is that, one, it's made all of this work much better. It's created far more opportunities for doing inductive transfer. It really woke the community back up on inductive transfer. And it's created all sorts of new methods for doing it, because deep learning is now a complex collection of different methods all by itself. And each of these presents different opportunities for inductive transfer. So it's really exciting that all of this inductive transfer has a new lease on life thanks to deep learning, and is working better than it ever did. Just want to give you an idea of what people were thinking back then. Rich Sutton, who many of you know from reinforcement learning, way back in '94 at a constructive induction workshop, which we don't even have that many constructive induction meetings anymore, says something like, everyone knows the key to good representations, that good representations are the key to good learning performance. People learn really fast because they start with good representations when they start learning. The standard machine learning methodology is to learn one concept at a time. This is not the way to do constructive induction. Instead of doing one concept at a time, we really should be learning multiple things at the same time. If you came to the next task with an excellent representation learned from the preceding n-1 task, you would learn faster and better than you did before. So even someone who's not working in inductive transfer, Rich Sutton, is talking about these sorts of ideas at a constructive induction workshop as early as 1994. Let me give you a personal story. This is the origin of multitask learning. This is how I started working on this. So I had two advisors at CMU when I was a grad student back in the early 90s, Tom Mitchell, who does supervised learning, and Herb Simon, who at the time was working on scientific discovery. Herb, by the way, is one of the grandfathers of machine learning, artificial intelligence. So he's one of the luminaries from the early days of AI. Okay, so while working, hard to try to come up with a thesis topic, one day I asked myself, how would I try to do something like scientific discovery, what Herb was interested in, using neural nets, or the kind of things that Tom Mitchell was interested in? How would I use supervised learning to do scientific discovery? It seemed like a crazy question. It didn't seem to make sense. Scientific discovery is all about learning succinct mathematical laws. Supervised learning is pattern recognition and curve fitting. It is anything but succinct, especially now. How does massive curve fitting, fit in with learning succinct mathematical laws? So, here's the question: how would a neural net learn something like the universal law of gravity, or Kepler's laws of motion, or, PV equals nRT, or any of these nice, simple physical laws? So, here the universal law of gravity is a constant times the mass of the two objects that are gravitationally attracting each other divided by the square of the distance between them. So my thought was, well, maybe a neural net that gets information about the position of the moon in its complex orbit around the Earth, maybe that neural net would be able to learn something about the orbit of the moon. And in fact, given enough data, I'm confident that this would work. However, what the model is going to do is it's just going to learn some complex curve fitting that represents the rotation of the ellipse and things like this. It's not going to come up with a general law like G m1 m2 over r squared, even if we were to give it things like the masses and sizes of the objects and all that sort of stuff. It's not going to learn the general principle. And that's because in this example, the masses of the objects are fixed. The radius is relatively fixed. It's not going to learn something general. It's just going to curve fit the problem and then do really well if we give it enough data. So my thought at the time was, well, maybe if I had it learned about multiple gravitational systems, all of which were different. So here's the inner planets circling around the sun on the left. On the right, here's the outer planets circling around the sun. Suppose, and each of these things, like Saturn and Jupiter have many planets. Suppose I were to give a neural net many tasks. And one was predicting the orbit of the Earth, one was predicting the orbit of Venus, one was predicting the orbit of Jupiter, one was predicting the orbit of the moons around Jupiter, one was predicting the orbit of the moon around the Earth. Suppose I gave it all of these different tasks at the same time. Maybe there'd be a better chance that it would generalize and learn to learn something more like a law, something that was more generally true. And then, maybe I would even throw in like small things like, gravity operating on the Earth, or gravity operating on asteroids and comets and things like that, gravity operating on galaxies. So the more diversity in tasks that I could give this neural net, the better the chance that it would be forced in the common shared hidden layer to learn something that was truly general and, let's say, more law-like. So that was the idea. So I decided the only way to learn general laws was by learning about many different systems, all that shared, let's say, the same physics using a common hidden layer. And if the model's biased to share this representation, then it might learn something that's general. But all the experiments I could think of for doing this were very contrived because I kind of already knew the answer. I mean, I already knew about gravity and Kepler's laws and things like that. And, you know, it's hard to set your sights on, you have to learn a new law to succeed in your thesis. You know, new physical laws are not that easy to come by. So I decided this was very, very difficult. And I just started thinking in general how multiple tasks in supervised learning could help each other if they were using a shared representation. And that's how multitask learning was born. So, and I never, ever ended up doing work on scientific discovery, even though that's how I started thinking about this. And instead, I focused on supervised learning and focused on things like how should tasks be related to each other? How can they help each other, harm each other? How does this multitask learning actually work? What's the mechanism inside the neural net that makes it work? How do we make it better? How do we do it in other things like not only neural nets, but k-nearest neighbor decision trees and stuff like that? So that's how I got interested and ended up working on multitask learning. It's really because I started asking a stupid question, which was how would we use supervised learning to do scientific law discovery? And then one thing led to the other, and that's where multitask learning came from. Now I'm going to talk about some massive, very large scale multitask learning that we've been doing. This is kind of fun. And, you know, multitask learning by the end of my thesis was working well in many applications, but it did not scale well to large numbers of tasks, that is hundreds or thousands of tasks. And most of the test problems I could think of for a large number of tasks seemed very artificial. You know, I had to sort of make them up as opposed to natural problems. So I was looking for a real problem that had very high task dimensionality, where multitask learning would make the difference between success and failure, not just a tiny increase in accuracy. My idea was in the late 90s, let's do massive multitask learning weather forecasting. Let's try to predict weather at every point on the surface of the Earth, all at the same time. So at every point in this grid, we're going to predict the weather all in parallel. These are all going to be outputs. We're going to try to predict all the variables at the same time, you know, temperature, precipitation, cloudiness, wind, and we're going to try to predict at all scales going forward at each of these grid points. So we've got, let's say, 1 degree resolution, which is actually very coarse for weather, but let's start there. That's 64,000 output locations. We've got maybe a dozen weather attributes at each location: temperature, rainfall, pressure, things like that. Maybe 10 time steps into the future: 8, 16, 24, 36, 48, 60, 72 hours. So that gives us, you know, on the order of 5 to 10 million output tasks. And what's funny is the number of input variables is really going to be somewhere between, say, 100,000 to less than 1 million. So we've got somewhere like 10 times to 100 times more outputs than inputs. So this struck me as a really exciting natural use of massive multitask learning. And clearly points on the grid are related to each other if they're adjacent to each other, and they're similar to each other if they're similar at different time scales, like 8 hours is similar to 16 hours. And some of the variables are also similar to each other. There's, you know, some correlation between things like barometric pressure, rainfall, and wind speed, and things like that. This is really crazy idea, though. You know, replace 100 years of research in physics. What is thousands and thousands of PhDs for building weather simulators? Replace it with multitask learning. So why is this a bad idea? Well, right now, the physical simulation they do uses the largest supercomputers on the planet. They've done fluid dynamics, conservation laws. They know all about physics and fluids. They use intense math. They use huge computers. And we haven't even seen all of the phenomena in weather, right? The weather this year might look different than the weather has in the past 10 or 20 years. So, you know, how can you really hope with machine learning to sort of predict the weather? Do you really have a chance of doing this accurately without knowing all the physics before you start? But it's even worse than this. It turns out you don't have that much data. We've only got 20 to 40 years of data. 365 days a year, it might sound like a lot, you know, it's about 15,000 days, but it's not as much data as you think, especially not for deep learning. because like October 1st at each point in the globe only happens once per year. So if you got 20 years of data, you've only got October 1st 20 times in your data set. And yes, October 2nd, and October 3rd are kind of similar to October 1st, but they're not the same. So you really don't have very much data, and the weather really changes pretty rapidly from day to day. So it turns out you're very data poor when you try to do this. But why is this a good idea? Why did I think this made sense for multitask learning? Well, for exactly that same reason. You don't have much data, and yet clearly the variables we want to predict, the adjacent points on the grid, and the different timescales, clearly these things are all related to each other. So the weather can't be super different typically, 12 hours into the future and 16 hours into the future and at adjacent grid points. There's strong relatedness between these adjacent tasks. So you don't have enough data really to train a single task model on any one point in the globe and for any one variable like temperature, but you might be able to do this with multitask learning. So the adjacency of these points is really, really important. And the adjacency of the points in time is also important. And then the hope that these variables are all strongly related to each other, because weather is a complex multivariable physical phenomena. The hope is that it's the similarity of all of these things that would make multitask learning suddenly work. Hey, I did a back of the envelope calculation in 1998. It said, there's not a chance this is going to work. The data only went back then about 20 years. The data was difficult to get. You couldn't get global data. The data was small as far as a neural net was concerned, but it was still very big for disks and for modems. We didn't have GPUs back then. I didn't know that one hidden layer really could do this. I thought it was unlikely one hidden layer would work, but nobody had multiple hidden layers working at the time. We all tried, but we all failed at that time to get it to work. And I got to tell you, I didn't even know about convolutional nets at this time, even though they existed. And it's clear these nets need to know about physical temporal adjacency. And you really need convolution or something like that to make that work. Hey, I tried it again in 2006. I got myself invited to the American Meteorological Society meetings. I was an expert at the time in ensemble learning, so they were very interested in ensembles. In fact, the meteorologists were working on ensembles really before we were in machine learning by taking average predictions from multiple forecasts. So I got invited to these meetings to see if it might be possible. Back of the envelope calculation, still too little data, too little computation. Nobody had done anything even approaching this. It just still looked too hard. Then 10 years later, I found an intern who does deep learning for science, and I convinced them to work for a summer on deep weather forecasting. We sent a bunch of disks to NOAA and a bunch of money, and they sent us 35 years of data for North America. We still couldn't get data for the entire world. We put together the biggest GPU machine we could. North America was still too big to work on this system, so we just worked on the Pacific Northwest. And we tried everything we could, different convolutional architectures, different training methods, different parts of the country, predicting different variables. Nothing worked. Occasionally, we would get parity with physical forecasts for some variable, for some region, for some period of time, but it did not really seem like it was working. It just didn't look like it was plausible. And often the forecast didn't look physically real, like they were a little too extreme in some cases, which maybe now is good that we're having more extreme weather, but at the time it looked like they were too extreme. The internship ended, I'm sad to say, without any success. We had no papers and no obvious ways or ideas on how to do it better. Maybe if we kept working for a few years, we would have been able to get it to work, but we did not get it to work at that time. 2 years later, I called Dale Duran. He's the Dean of Atmospheric Sciences, Dean of Weather Forecasting in some sense at UW, which is a university around the corner from Seattle and Redmond. And I said, I had this crazy idea. I went to a meeting with Dale and one of his grad students, Jonathan Ween, who was interested in machine learning, but he's a atmospheric science weather grad student. He's a physicist. And I explained the crazy idea I had to Dale and Jonathan on the Blackboard. And Dale just said, wow, that's interesting. It's a crazy idea. It'll never work. Uh, but hey, you seem like an interesting guy who's interested in some of the stuff. You've been thinking about some of our stuff. Would you like to, work on some other collaborations where machine learning might actually be useful in weather forecasting? And I said, sure. This is how fun collaborations often begin. So we started meeting regularly to discuss possible projects. And Jonathan, since he was interested in machine learning, was involved in all of those meetings. And then one day I got a call from Dale. And Dale said Jonathan was taking a machine learning class. And as a class project, he decided to train a deep neural net to do weather forecasting. And the crazy thing is, it was working much better than Dale ever thought. Dale basically said, Rich, that crazy idea that I said we shouldn't work on? It's working. Come back for a meeting. So I went back for a meeting, and one thing led to another. We've now got multiple presentations and papers on can machines learn to predict the weather without using physical simulation. Jonathan, most of this became Jonathan's thesis. Most of this is first authored by these guys because most of it is published in atmospheric sciences journals, not in machine learning conferences. So this is really exciting. And it's led to 3 really successful papers in journals of atmospheric science. And these papers are getting a lot of attention. In fact, 2 of these papers are one of their heaviest download papers from the journal. So they're really getting a lot of interest in the weather forecasting community. Let me just briefly show you how that works. So we've got this sphere, and what weather people do is they don't try to do complex spherical geometry on the sphere because they have to do expensive calculations in their physical simulators. So what they do is they break the sphere up into faces, and they do what's called cubing the sphere. So, and they break the sphere up into the northern cube, the northern face, the southern face, and then 4 faces that run east to west. And then what we're going to do is train a neural net so that it's learning the same function for the northern face and for the southern face, except that the rotation has to be reversed. And then we're going to learn the same functions for each of these 4 faces that runs around the middle of the Earth. So that's roughly our setup. We're going to use a UNet architecture. And the bottom of the UNet architecture is to sort of learn large scale information. And the top of the UNet architecture is to learn fine scale information. It turns out both of these are critical for weather. There are huge wave phenomena that are the size of continents and oceans that you have to learn about to do good weather forecasting in the long term. And then there's very local fine detail affected by geography that you also have to learn about. So you have to learn about both coarse scale and fine scale to do it. So this is what one of our architectures look like. And what goes into the model is going to be the state of the weather for the entire globe at a single point in time and all the variables that we have access to. And then the model is learning to predict what the state of all of those variables is going to be, say, 8 hours from now, 16 hours from now, 24 hours from now, that kind of thing. So that's what our architecture is. And in fact, we don't try to predict all timescales at the same time. It turns out that's too hard to learn. So instead, what we do is we try to predict the next few major timescales, like 8, 16, 24, 32, things like that. And then we roll the model forward. That is, if we're interested in making a prediction that's a week out, we take the prediction, say, from a day into the future, put it back into the input, and then we get a prediction for 2 days into the future, put that into the model, gives us a prediction for 3 days into the future. So we roll the model forward. Now, these are the number of trainable parameters. It's only 2.5 million trainable parameters. This is very small by deep learning standards. But for us, this is a fairly big model, given that we don't have as much data, as I said, as you might have thought we would have for weather forecasting. So this turns out to be a pretty big model for us. And it takes us about a week to train this model on a powerful GPU. This is a single GPU. This is not parallelized across multiple GPUs. And this is epochs across the x-axis here. The blue line is the loss on the training set. You can see that nicely goes down. This is squared error of your weather prediction across the entire globe, across all variables that you're predicting. So you can see that the squared error is going down beautifully. We do some special kind of tuning at the end. That's why there's a little sharp jump right here at the end. Once we know we're we're getting to the end, we do a little more. And you can see we stop before we really get there. And that's because it takes another week to go this extra little bit to get it flat. So we stop, like a lot of modern deep learning, we stop before we've actually really hit the optimum and started to overfit. And you can see our validation set, has pretty similar accuracy as the train set. So it's pretty closely approximating the train set accuracy. And that's really good. It means we are learning something. Let me show you what a forecast looks like. So this is going to be a 6-hour roll forward forecast from our deep learning model on the left. And on the right is ground truth. It's the real world. So I'm going to play this little video for you, and you can see what the forecast is doing as we roll forward. So we roll forward from 6 hours all the way out to 78 hours. Okay, so we're rolling forward multiple days here. And there's a lot of similarity. What the atmospheric scientists were really excited by was not only is the model pretty accurate, but it looks like it's capturing the phenomena reasonably well. It's not learning crazy hot spots or cold spots or places where the wind is 300 kilometers an hour, things like that. It actually seems to be doing the right kind of thing, which is really remarkable because, in fact, a lot of the physical simulation models do actually, after many days, start to go off the rails. They start predicting things that are not physically plausible, and they have to use special techniques to keep the physical simulation within the range of what's reasonable by constantly looking at historical data and finding like nearest neighbors in historical data to bring the physical model back to reality. And we've been able to train these neural nets so that doesn't happen. And that's because of multitask learning that this is working. This absolutely would not work with single task learning. So anyway, that's kind of success. Here's a model. This is forecast day. This is out to 2 weeks on the right. This is squared error on the vertical axis. So down is good. And you can see everybody is good if we're only predicting, a few hours to maybe a day into the future. The green line is us. This is our deep learned ensemble method. The gray line is climatology. So climatology just means, hey, predict on October 1st what happened on October 5th the last 20 years. So you just sort of predict what the average weather was at that date, time, and location for every date, time, and location. So that's a pretty good model. It just sort of tells you historically what the weather was, and that's what you predict. And you can see it's not a great model, especially for short-term forecasts, but it's okay in the long run. The red line is really exciting. That's ECMWF. That's the European Model Ensemble. It is currently the most accurate model for predicting weather, especially long-term in the world, significantly more accurate than the North American model. In fact, our model is pretty close to the North American model. And then this purple line is persistent. So basically, you predict that the weather tomorrow will be the same as the weather today, or that the weather 4 days from now will be the same as it was today. And you can see that persistence quickly gets worse even than climatology after just a few days. Just predicting that the weather is going to stay the same is not a good idea. So what's exciting is that we're actually doing very well. There's about a 3-day gap between the accuracy of the world's current best model and our model. And that's amazing for multiple reasons that I'll explain. And as I said, the NOAA model is not as good as this red model. So there's only like a 1.5 day gap between this deep neural net and the NOAA model. So it's really kind of remarkable how well deep learning is working, again, thanks to inductive transfer. This is a different way of looking at it. This is 3 weeks into the future, 4 weeks into the future, and 5 to 6 weeks into the future. So this is what's known as S2S, sub-seasonal weather forecasting. And it turns out being able to predict a month or two from now what the weather might be is really, really important for many industries and for things like the World Health Organization, who are trying to get food around the world, vaccines around the world, and things like that. So it turns out being able to know a month or more in advance helps you determine things like what should you plant, when should you harvest your crops, when would it be bad to travel, all those sorts of things. Now, bars that go further to the right are higher accuracy here. And you can see in very short time scales, the ECMWF ensemble is doing very well. We're not doing bad. And persistence, of course, is a good baseline, but it's not doing very well. And persistence gets worse as time goes on. But notice that the neural net, the deep neural net, multitask neural net, is catching up relative to the ECMWF model as we get out to 4, 5, 6 weeks. And that's remarkable because this is very, very important. Also, our model only takes minutes to make a prediction, whereas this ECMWF model, it turns out this model takes many hours on some of the world's largest supercomputers to make a prediction, whereas our model on a single GPU is making a prediction in minutes. And that means our model can be used for things that this model can't, the ECMWF model can't practically be used for. And I just want to show you, this is our model in the middle. This is ECMWF on the left. We're only using 6 fields from the atmosphere, and we're only looking at a 2D version of these, whereas ECMWF is looking at 9 fields, and it's got 30 3D versions of these. It's got 91 vertical levels that we don't have access to. So they have much more detailed information. ECMWF has much finer resolution. Okay, they're doing 18-kilometer cells. We're doing 150-kilometer coarse resolution. We have only 3 inputs coming in about the rest of the world. They have many physical parameterizations. We don't have any coupled models with our model. It's just trying to forecast the weather, whereas their model knows about the state of the ocean, waves, it knows about sea ice and all those sorts of things. Our model, we aren't able to perturb the initial conditions as many ways as they do. But we still managed to make an ensemble that's larger than them by perturbing the CNN weights, which is really, really exciting opportunity. They have to do some very heavy lifting computationally to do this. So anyway, we're not yet as accurate as ECMWF, but it's only been a few years, whereas weather forecast has had 100 years, and we're not that far behind. And our model doesn't have anywhere near as much information or as much resolution. So it's really amazing that we're even able to compare ourselves with these other things. And it's sub-seasonal timescales, 4 to 6 weeks. It turns out we're already a useful model, and we have some advantages that the physical simulation models don't have. And this is just really exciting stuff. It's getting a lot of attention from atmospheric scientists. We can't believe that this crazy idea of replacing lots of well-studied physics with simple deep learning could work, but it's only working really because of multitask learning. It really is this massive multitask learning thing. And it's really exciting. We can do lots of ensembles of these things, and it's still very early days. Every time we figure out how to include more data, finer resolution, make the model consider more things, it does better. So it's still very early days in this research. Okay, now I'm going to wrap up by talking about some work we're doing in editable, intelligible glass box multitask learning. So this is joint work with a number of people, including Jeff Hinton at Toronto and Google, some people at Google, and some other people at Microsoft. And this was a paper at NeurIPS a year ago. So let me give you an introduction, a very high level, to generalized additive models. So you've probably heard that there's an accuracy intelligibility trade-off. Deep neural nets are not very intelligible, but they're really accurate. And things that are intelligible, are not very accurate, but of course you can understand them. Hey, if you're working with what we would call tabular data, not pixels, not raw speech, but tabular signals like a person's blood pressure, their age, their income, their education. If you're working on that sort of thing, this trade-off doesn't exist anymore. And that's because we now have these generalized additive models. EBMs is a boosted, explainable boosting machines, and NAMs are neural additive models. Both of these things train glass box models, and they're just as accurate on most tabular data sets as deep neural nets. And yet they're even more interpretable than like linear regression, logistic regression. So here's the simplest additive model. It's a linear model, or pass it through a sigmoid if you need to do probabilistic classification. Gold standard for interpretability, not very accurate on complex data sets because it can't model nonlinearities. And sometimes, by the way, this even gets the sign of coefficients wrong. And that's because a linear model can't fit a complex nonlinear data set. So it has to trade off errors on different terms, and it'll even get the coefficient, the sign on some of those coefficients wrong. And that's a terrible thing. It might tell you that this makes people more sick, when in fact it doesn't. It makes them less sick, and it might even get the sign on these things wrong. So this is actually a dangerous model to use because it's poor fit to complex data means that it really doesn't get things right all the time. The other end is, deep learning, black box learning. Obviously not interpretable, but it can be extremely accurate because it can model nonlinearities. It is, however, if you do black box explanation like SHAP to try to understand what's inside this model, it is learning overly complex functions. It's more likely to learn spurious effects. In the middle, we have these things that are called generalized additive models. These were invented by Trevor Hastie and Rob Tibshirani at Stanford in the late 80s. Statisticians invented these before most of machine learning happened, before the internet happened, right? This has been around a long time. And these explainable boosting machines and NAMs, neural additive models, these are modern recreations of these GAMS methods using modern machine learning techniques. And it turns out these are more interpretable than linear models because they can model nonlinear effects and that they can show them to you in these graphs, which are very easy to understand to an expert. So they really can represent the phenomena with high fidelity in a way the expert understands. Because of this ability to model nonlinear things, they can be very accurate. And in fact, the surprise is that these things really can be on tabular data as accurate as the black boxes. That's really a shock. These things tend to be these univariate functions plus a small number of pairwise interactions. And it's really kind of a shock that a model that is that restricted can compete in accuracy with much more complex things like deep neural nets. And then importantly, because this model class is restricted, it's much more likely to show important effects. That is, it's less likely to learn spurious effects, and the things that it shows you on the graph are much more likely to be real. Let me just give you some evidence that these are high accuracy. This is EBM, so this is boosted machines, not neural nets, in the first column here. And the average AUC on the 10 test sets, 10 test problems is 0.866. And on the right, we've depth optimized gradient boosted trees. And it turns out their average accuracy is also 0.866. And we get a very similar story if we use NAMs here instead of EBMs, and we use deep learning here on the right instead of gradient boosted trees. So it turns out we get very comparable accuracy on these data sets in AUC if we're looking at boosted trees that are glass box versus black box boosted trees, and the same sort of results for neural nets that are glass box versus neural nets that are black box. So now the question is, well, how do you make a neural net be glass box? So here's what we do. We have a deep net, subnet, which is only allowed to see feature X1. Notice there are no cross connections between any of the other features and this subnet. So this subnet is restricted now to learn a function only of X1. At the same time it's learning that, this subnet is learning a function only of X2. So every feature is going into a deep net, but that deep subnet can only learn functions of one feature at a time. And we can easily generalize this if we want some pairwise interactions, like a pairwise interaction between X1 and X2. We can create another subnet that has only two inputs to it, X1 and X2, and now it'll be restricted to learning only a function that combines feature X1 and feature X2. And then if we're doing classification, we go through a summation here, and then we go through a sigmoid for classification. And if we're doing regression, we don't have this sigmoid unit. So if you think about it, this is, an additive function, right? It's a function of X1 added to a function of X2, added to a function of XK. The predictions each of those functions makes gets added together, and then you go through a sigmoid if you need to. And then the cool thing is, like, this isn't interpretable yet, right? Each of these is a deep neural net that you don't understand. But notice that each of these things has a single input and a single output. That means we can take one subnet, we can sweep through the inputs, see what its output is, and that means we can draw a graph of what the response of the subnet is for the input feature. And that means we can take each of these subnets and we can replace them with graphs. And these are exactly the kind of things we're looking for. These generalized additive models are typically viewed as graphs, like I showed you before. So, and we can now have this deep neural net, which is composed of many subnets, one for each of the input features, and then one for each pair of features that we want to model. And we can have each of these things learn something which can then be represented as graphs. So now it's fully interpretable. So we can really understand exactly what this model has learned. And in fact, what we usually do is we throw away the neural net after we generate the graphs, because the graphs are going to make exactly the same prediction that the subnets would have made, right? So we don't actually need to keep the hidden units or anything around. So suddenly this becomes a really compact, fast model. So what I want to show you, though, is that this is exciting and this works. And I'm not going to tell you more about that. If you want to see this, go to the paper. What I want to show you is that we can now do multitask learning with this, which is really, really cool. So let's do multitask learning with neural additive models. So here's a single task network, right? This is the same architecture I showed you before. Each feature goes into its own subnet. They all get all the subnets get summed together. They go through a sigmoid. For multitask learning, we need to have multiple outputs. So now I've got 3 outputs. Notice that I still have the same number of subnets, but each subnet is now connected to each of the 3 outputs. And each output can learn an independent weight to each subnet. And also the gradient coming from each output helps form the graph that's going to be learned by each of those subnets. So that's kind of cool. And it can turn out that, you know, one output puts large weight on this function that's learned, but maybe the second task puts low weight on it, or even puts negative weight on it, inverts it, or something like that. So it can turn out that these things don't have to learn the exact same output function because they can put different weights on these subnets. It turns out that's still too strong a form of sharing. So instead, what we do is we have multiple subnets all being trained for feature X1 and multiple subnets all being trained for feature X2. All of these things, all of these subnets are connected to task 1, to task 2, task 3, task 4. And now what happens is task 1 can, if it wants, say, you know, the subnet 1 for feature X1 looks really good to me, but subnet 2 and subnet 3 for X1 don't look good to me. And it could put low weight on 2 and 3 while putting high weight on 1. Or maybe task 2 and task 1 both want to put equal high weight on what's being learned on subnets 1, 2, and 3. They're all just learning essentially the same function, just noisy versions of each other. And maybe you just want to average them. And maybe task 1 and task 2 completely agree on what they should predict. Here's the cool thing. Remember, I said you can replace each of these subnets with a graph. So now we'll have 3 different graphs for X1, 3 different graphs for X2. But because this is a linear weight that's combining these graphs for task 1, a linear combination of graphs is still a single graph on that feature X1. So it turns out we can take these weights and we can draw the graph that task 1 likes for feature X1. And we can draw the graph that task 2 likes for feature X2. And there's a strong bias, because this is multitask learning, that these things will learn similar graphs where they can, but they now have the ability to learn different graphs or variations on the same theme if they need to in order to be accurate, because not all tasks need to learn exactly the same thing. So this really works incredibly well. Let me show you, this is synthetic test problems, and then I'm going to wrap up. So there's 6 different tasks, all defined on these basis tasks at the bottom. So this is X0, 1, 2, and 3 at the bottom. So basically the way to think of it is task 0 is function of X0 plus G of X1 plus H of X2 combined. So for task 0 to do well, it has to learn in its neural net to learn this function of X0, G of X1, and H of X2, and then it has to sum them to do task 0. Each of these tasks, this is a very contrived synthetic problem, each of these tasks needs to learn different variations of these same basis functions from the input features. Now we can train these tasks single task. We can just have one neural net learning task 0, another neural net learning task 1. And it's sort of a shame they weren't trained together, because task 0 and task 1 both share f of X0 and G of X1. So they would benefit from training together if they could. So here's what we get. So the top is the squared error performance. So down is good. And notice when we train single task NAMs, these are additive models still, so they're interpretable, but they're only being trained one neural net on task 0, a completely separate neural net on task 1. Notice that the squared errors are all around, let's say, 1 for single task learning. And then when we do multitask learning, notice that the squared error on all of these tasks, so now this is one neural additive model that has multiple subnets. Now this thing is being trained on all 6 of these tasks at the same time. And we've contrived it so these things have similar substructures. So it makes sense that this would work. Notice that the squared errors are much, much lower, right? They're around 0.7, which is great. So we've got like a 30% reduction in error here. And here, if we look, these are interpretable models, so we can look at what they've learned. If we look at what task 0 has learned, it's learned part of the functions well, but it's also screwed up other parts of the function. Overall, it's not very performant. The multitask NAM, however, has done a very good job of learning these functions. And if we look at the subfunctions that it has learned, because they're interpretable also, it turns out that the subfunctions are much more true to the original subfunctions F, G, H, and I that I have here. So it turns out this really does work, at least in synthetic data. Let me show you a real example, and then I'll go to the summary slide. This is a COMPAS data set. We're predicting recidivism, which is the chance that a person in the criminal justice system will commit another crime. And this is being used to make decisions about, say, bail or whether the person should get parole or not. And there's been lots of discussion, say, starting 5 years ago, on whether these models are racially biased. That's where you've probably heard about this. So what we can do is we have both men and women are in this data set. It's about 3/4 men and 1/4 women. And we can train a single task neural additive model on, say, just women, on just men, or we can pool the data and train it the way it's usually done, combined. And these are the kind of accuracies we get. High would be good, that would be higher AUC. And notice that we do more poorly on women than we do on men, and that's because men are 3/4 of the data set, so we have a more sample size for them. And we do better, actually, if we pool all of the data together into a multitask, into a single task network. However, if we do multitask learning, that is where we're a separate output for women and a separate output for men being trained in parallel on the same network using these combined subnets that are explainable, it turns out we get higher AUC for women, significantly higher because it's benefits from being trained with the men. And we get a slightly higher accuracy for men as well. And we get a combined accuracy that's slightly higher too. Now, these differences in accuracy are not huge. If we just had more data, we could, of course, achieve higher accuracy. What's really exciting, though, is to be able to look at the graphs and see what it has learned. And there's a real difference between a model that's being trained on all people, men and women, versus a model that's doing multitask learning on men and women separately. So let me show you. This is charge degree. This is one is a felony on the left. This is a misdemeanor on the right. And notice that if you do a single task NAM, it learns that having a felony puts you at higher risk of committing another crime than having a misdemeanor. Notice that there is a small separation between what's learned for men and learned for women. They're not exactly the same. The risk of committing another crime, another felony, is higher for women, but lower for misdemeanors. What's really, that's not that big of a difference, though. That's not that exciting. This is what's really interesting. This is risk as a function of race. And this is the kind of graph we've seen from many other people's research, as well as our other prior research. And we see things, for example, that whites are lower risk than African Americans. That's what a lot of people have talked about. Here's what's so fascinating is when we do the multitask NAM, we see that there's a fairly different risk associated with races for men and for women. And this sort of shows that doing multitask learning is probably a much fairer model to use for men and for women, and it's more accurate. So it would make a lot of sense to do this. And now, for the very first time, we can see what's being learned by these models. Hey, inductive transfer multitask learning, it has a long history that even predates deep learning. And of course, now that deep learning is here, it's working even better, and there are many more ways to use it. So that's just really exciting. Weather forecasting is currently, we believe, the most massive use of multitask learning, and it's working surprisingly well. We really can't believe that it's working as well as it is working. And we're nowhere close to the complexity of the models that we're competing against yet. So that's really exciting. There's a chance we're going to catch up with those models. And on tabular data, you really can train these glass box models that are just as accurate as black box models. So if you're working with tabular data, you should not be using deep neural nets or gradient boosted trees anymore. You really should be using NAMs, neural additive models, instead. And by the way, we don't know how to do multitask learning with the boosted trees, with the EBMs, but we do know how to do this glass box learning with the NAMs, the neural additive models. So for the very first time, I've been working on multitask learning now for 20, 30 years, I guess. And now for the very first time, I can train complex multitask learning models and actually understand what they're learning and what multitask learning is doing. And this is opening up new opportunities. Okay, I just want to say thank you. So let me pause and I'll stop sharing my screen.
Are there any questions? If you have a question, please come to the mic.
Hi, Rich. Thanks for the talk. Hey. It was great storytelling. So I wonder, in the methods you've described, all the tasks always firing all of the neurons in the neural network. So I'm thinking in some settings, you might be doing only one task at a time. So I'm mostly thinking about like reinforcement learning problems. Do you think in those settings, you would want to instead fire sub-networks within a bigger network? And if so, how would you go about that?
It's a great question. And we even did some work back in the early and mid 90s where we had outputs that were basically mutually exclusive. And by mutually exclusive, what I mean is that maybe we're trying to predict risk at 10 different hospitals. And then every patient is only in one hospital. They're not in all 10 hospitals. So you only have a training signal for any one output at a time. And that works fine with multitask learning. You can do gradient descent, and there's no problems with that. You have to do some tricks to make sure that you don't hurt the 9 outputs that don't have a signal by not feeding a gradient back there. But that works fine. Now, in that case, all the neurons are still firing for every output task. It's just that that output task might be putting less weight on some neurons than other tasks would, and vice versa. But now that we have these NAMs, the neural additive models, where we really have a notion of subnet, now if you had different outputs, some of which had low or zero weight to some of the subnets, those subnets really could not fire at all, and that would work fine. Also, there are situations where you don't have some of the features, and it turns out an additive model, a regular neural net, if you suddenly don't include an input feature and you don't do something clever with that input, like impute it with a mean or something, a regular neural net breaks. It turns out the additive models do not break if you're missing some of the input features. They just get less discriminative because they have less information. And that's because of the additivity property. So there's no complex interactions between all of the inputs at every hidden unit. And it turns out because of that, you can be missing some of the inputs for any one prediction you need to make. And then some of the subnets don't fire at all because they don't have an input. And that's perfectly fine too. Yeah. Thanks for the question.
Thanks.
Okay. There are a few questions in the chat. So like one question, which was probably from the middle of your talk, is like, did you predict this extremely hot summer anywhere on Earth?
Oh, that's a fun question. Actually, I have to admit, we haven't done any predictions that run to the present time. We're always, we're scientists, so we're always using our models to predict what is still historical data. So what we tend to do, for example, is we will train on the first 20 years of our data. We'll validate on maybe the next 5 years of our data, and then we will test on the last 5 years of our data. It's very important to do that sequential kind of train validation test set split up for weather forecasting, just like it is for the stock market and things like that. So we never actually used our model, as far as I know, to make predictions for the current summer. It's a wonderful question, though. Like maybe one thing we did do is there are annual weather forecasting competitions, just like there are, in protein folding and, all sorts of credit lending and stuff like that. And Jonathan has done extremely well. Now, Jonathan graduated a year or two ago, so this goes back a couple of years ago when he was working on his thesis. But Jonathan did extremely well. I think he won one of those competitions using our deep learning neural nets. And basically there you really are predicting the future, because the way the competition works is they give you the data up to a certain point in time, and then you have to make predictions and send them in for what's going to happen, say, over the next 3 months. And then they actually wait until those 3 months happen and compare. So we have done a little bit of stuff on actual future forecasting for these competitions, but I have to admit it hasn't been our main focus. Since our goal, we still have so many things we need to do to get more information into these deep models and make them still fit well, despite the fact that as we add more variables and add more complexity, we'd never get more data. It's not like time is rolling forward quickly. So we still have only 2 or 3 decades of worth of data, and that's our limiting factor right now. Great question, though.
Okay, a related question. So have you analyzed your weather prediction model in terms of non-stationarity? So how well would your model trained on data from 1980 to 2010 generalize to the last decade? So how does this compare to simulation-based models?
Right, and that is exactly how we do it. So we train on the first 10 or 20 years, validate on the next, say, 5 years, and then make our predictions on the last 5 years. And that's how most people in weather forecasting work. It's very problematic if you just randomly subsample your days and create train and test sets that have days next to or bracketing a day you want to make a prediction for in the test set. So that's how we do all of our validation, not only in the machine learning community, but also in the weather forecasting community at large. Your intuition is exactly right, that you need to do it that way. Hopefully I understood the question correctly.
Hey, thanks for the really great talk. Do you know how the neural additive models do in very low data settings? I imagine that the subnetworks could still have a lot of parameters.
This is a wonderful question, and we're doing a couple different studies on that right now as we carry the work forward. It turns out it does better than you would think in low data settings, and that's because the model is restricted to being simple in a way. Because in the simplest case, it's just learning a function of feature 1 and a separate additive function of feature 2. That's a tremendous restriction compared to a neural net that has full cross connections across all of these features, and thus is trying to learn something much, much more complex, higher variance. So it turns out it's not the number of parameters that count so much in the NAMs. It's the fact that the NAMs are a great restriction on the model class that's ultimately being learned. Now, there is one issue, which is almost the opposite of what you're saying. And if you read our paper, you'll see we struggled with this, which is, if anything, the NAMs were learning functions that were too smooth and too simple when they had only single inputs going to each subnet, and we wanted them to actually be a little twitchier. So we had to create a thing called an XU, which was an exponential hidden unit activation function, to actually make the NAMs be more likely to overfit. And then we do things like dropout and weight decay and ensembles to bring the overfitting back under control. But if anything, we found that the NAMs tended to be too smooth and simple, as opposed to overfitting, independent of the number of hidden units that were in the subnets. So really interestingly, we had to do some extra work to get them to overfit, as opposed to what they were doing naturally, which was underfitting. So I'm glad you asked the question. Yeah.
That's great news. Thanks.
Cool.
Okay, so there's another question about NAMs. Are NAMs another name for mixture of experts? Adding logits is equivalent to geometric mixing of predictors in probability space. Why then limit the experts to single feature inputs? Do NAMs get around the winner take all issue of MOEs?
Okay, so these are multiple questions. It is not the same as mixture of experts, although it's fair to consider them to be, similar to each other in some respects. Our experts, have to be experts of single functions trained in a specific additive way, and we go to great length to make sure that those individual functions have certain properties so that they will retain intelligibility. And then we also add, as I said in the presentation, a small number of important pairwise interactions. Those are also graphable. And then if necessary, we'll go to three-way interactions, but we typically won't do that. So you might think of them as being mixture of experts where we've carved the space up differently in order to have intelligibility, but they're definitely related to each other. And it's important, I carry this book with me. This is the original book on generalized additive models. And we are true to many of the ideas that are in this book. And this book is dated 1990. This is Trevor Hastie and Rob Tibshirani, statisticians at Stanford, who invented this stuff for all the reasons that we want to use it. And us using boosted trees or neural nets to do it is we're just using modern machine learning techniques to get these things more accurate so that now they're competitive machine learning techniques, whereas the original methods that they had available in the late 80s were not competitive. There were other questions there, and I'm sorry, I've forgotten what some of them were.
Do NAMs get around the winner-take-all issue of mixture of experts?
Yes. So there is no winner-take-all effect whatsoever in a NAM. I mean, they really are fairly different. An additive model versus a winner-take-all, is really very different. And it's not, I wouldn't think of the NAMs as being an ensemble at all. They really are learning different additive subfunctions. The only time they start behaving a little bit like an ensemble is when we start doing multitask learning in the NAMs and suddenly have 3, 5, 7, subnets for each feature. So we have multiple subnets for each feature that are then combined with mixing weights. And now you can start to think of this as being a form of ensemble because you have, you've learned like a stacking mixer, linear mixer. It has to be a linear mixer or else it doesn't make sense on top of the individual subnets that you've learned. Yeah, so it's still fairly different from mixture of experts, but I can understand why you're asking the question. Yeah.
Okay, thank you. Just two quick questions regarding the weather forecast. So you mentioned similarity between tasks. I'm wondering if the tasks are encapsulated one in one other or are just similar, because for the weather, for example, the temperature, variation in temperature, there is variation in gradients, variation which induces variation in pressure, and after that come, for example, the wind with strong non-linearity. So the tasks are encapsulated or similar. And the second question is for the long-term forecast. If we think about seasonal forecast or annual forecast, do you think that direct introduction of some physics that are within the numerical weather prediction, Navier-Stokes equations, would be feasible in the level of physics-informed neural network will be a good fit for long-term forecasts?
Oh, these are really fun questions. So let's see. It's as you're expecting. It's not the case that the tasks are encapsulated within each other, that you learn one first and then that helps you predict the next one. And then that helps you predict the next one. And that's because most physics equations are bidirectional. That is, the pressure affects the temperature as much as the temperature affects the pressure. So it goes both ways. So we're doing true parallel learning, which is great because that's what multitask learning is designed for, is true parallel learning. So there's a lot of similarity. Similarity is almost the wrong word. These tasks are definitely related to each other in the sense that they influence each other. And you're not going to have like a super precipitation event if you don't have low pressure. So there are some constraints also on these things, but they're really just sort of related to each other in a complex physical way. The physics of the atmosphere is incredibly complex. And I'm not joking when I say there are thousands of PhD theses that have sort of elucidated pretty good physics for this. And, most physicists who do weather forecasting are actually fluid dynamicists because it's a fluid phenomena. The second question, quickly repeat what the second question was. Just give me.
using the physics inside the neural network
yes.
itself.
Oh, this is a great suggestion. And there's even a little physics injected into our model in a weird way, which is, notice I had this uniform grid on the Earth and I had every variable measured at each grid. It is not the case that we have sensors spread around the Earth on a uniform grid. They're not sensors, in a grid on the ocean or even on land or things like that. So what happens is they take the data that they collect from all the sensor information that's available, and then they pass it into a physics model. And then the physics model spits that data back out for the grid points. And for all variables, even if you don't have them all measured, and even if you don't have them at all timescales. So basically, you can think of this as being physics interpolation of the available data. And then the input to our model, because it's hard to train neural nets on data that becomes available, isn't available, on a grid that's not uniformly spaced, all that sort of stuff. If you're trying to do convolution and all those sorts of things, it turns out the physics model is used as a way of washing, cleaning the data before we get it. So physics has already helped us in some ways. And we are trying to now inject maybe a little more physics into the model, although our main focus right now is adding more variables because we're still not using anywhere near as much information as the physics models we're competing with are using. But we do believe that injecting physics into the model might help it. Although we have to admit, we don't understand what the model has learned, right? This is not an interpretable weather deep model. So we don't know what it's learned. So we don't know what physics it might or might not be representing somehow inside, and therefore what physics we might be able to help it with. Or if we inject physics, we might force the model to think differently than it wants to think, and we might hurt it. So it's a complex thing going forward. But I'm sure this kind of thing is going to happen because there's a lot of interest now in this kind of model. And there's been research now by Google on doing short-term weather forecasting and things like this using neural nets. So there are other people who are starting to do this as well. We think there will be a lot more research going forward that combines both the physical side and the simulation side along with the neural net side. And one way to do this, by the way, is just make an ensemble of the predictions that come from physics and the predictions that come from neural nets. We're working on that as well. But there are other ways of doing what you're suggesting, which is more deeply injecting the physics into the neural net model. And I'm sure if we figure out how to do it, that will help us probably.
Yep. Hello, Rich. Thanks for the very interesting talk. So this question is again about the deep weather forecasting model. So I was wondering, what was the motivation for using cubing the sphere as kind of a pre-processing step instead of directly using 3D data?
Gotcha. It turns out the pre-processing and the post-processing that they have to do on the data going into the deep neural net and coming out of the deep neural net, it turns out that processing is really complicated. It also turns out that, all the grid points kind of converge as you get to the poles. And you don't want to be wasting lots of hidden units that are learning points that are very close to each other. You want the points to be sort of equidistant near the poles that they are, say, near the equator. And if you stay true to the way data is usually represented in weather and the spherical geometry, it turns out the pre-processing, the post-processing, and even how to sort of write code to generate the architecture of the UNet that we're using. It turns out all of those things are quite difficult. And in weather forecasting and simulation, the reason why they do cubing the sphere is because otherwise the spherical geometry that they have to embed in their simulators ends up costing them a lot of time. Like if you're going to do something trillions and trillions of times to do a forecast, you don't want to have to do like a sine or a cosine or a log or things like that, even if you're using fancy table lookup to do it quickly. So it turns out weather forecasters have been comfortable with cubing the sphere. That's how they've been doing things for at least a decade or two, maybe longer. So they were very comfortable because the people I'm working with are real atmospheric scientists. They were very comfortable with using exactly the same transformations for the deep neural net. And that way it's also an apples to apples comparison. Like nobody can say, oh, your deep neural net knows knows the spherical geometry better than the weather simulations. We're using exactly the same things. And I have to admit, it's not just to make it an apples to apples comparison. It's because it was much, much easier to get the data pre-processing, post-processing, and the neural net architecture, the convolutional filters. It was much easier to create all of those things on the cubed sphere. And then, as I said, we learned the same filters for each of the 4 faces that are around the equator. So it's actually learning the same thing, and then it's special coding tricks that makes it move over to being further east and then 90 degrees further east. And we learn exactly the same filters for the top of the globe and the bottom of the globe. The only difference is that rotation is in the opposite direction. If you take the top of the globe and put it on the bottom of the globe. I'm sorry, if you take the top of the globe and put it on the bottom of the globe. So we have to do special tricks to handle the rotation. And cubing the sphere just makes all of this easier to think about and get right. It's a really good question. I was surprised when they wanted to do this as well.
Sure. Yeah, great. Thanks.
Yeah.
Okay, I think we are 20 minutes late, so
Hey,
probably we'll wrap
I see
up.
a question from Danny Silver, so I'm guessing Danny is there. I just want to say hi to Danny. I mentioned Danny's work in the first slide. You know, there is a chance of these things doing lifelong consolidation. And now we might be able to see this because we have these NAMs where we can see what's being learned. So it's a great, great question, Danny. And Danny, I'm sorry I'm not there to say hello. Nice to see you again.
Okay, thank you, Rich. Let's thank Rich once again for this wonderful talk.
Thanks for sticking around.
Okay, so we will break for lunch now. So even though we are 20 minutes late, we'll try to start on time at 2:30 for our next keynote talk. So we'll see you again at 2:30.